right, we're going to go ahead and talk about the notes for chapter 8, part 1, and continued because I decided to separate this out and actually have a discussion about if a line is the appropriate model for our data. We do focus on that mostly this year, a linear model, appropriateness or not, but we'll later talk this year about what do you do if a linear model is not appropriate. But for now, we just establish, is linear a good fit? And we say why or why not, and then go from there. All right, so let's take a look. I have got some scatter plots, and then I have some residual plots. So if you can imagine these on the left, these 4 scatter plots on the left, these are your original data sets. Okay, so that's the graph of 4 different original sets of data. And then you go through the process and you make your residual plots. And so these 4 over here on the right are the, secondary graphs, the residual plots. All right, so where you have, your residual on the y-axis and here's your prediction line down the center and so on and so forth. All right, so what we want to do is we want to take a look at the data on the left and see which one of the residual plots it would create on the right. So here we go. Let's take a look at scatter plot 1. So when I look at scatter plot 1, and I've got the prediction line, I see that the points are tightly clustered nicely around the line here in the lower values of x. But as I get further out, look what's happening to the data. Seems to kind of like fan out and get further away from the prediction line. So I'm looking for the residual plot that demonstrates that. And it looks like here I've got data that's pretty close to the line, and then we start getting farther away. The farther out you get in X, the more wonky the data gets, and it's farther away from the prediction line. So, I would not want to be making predictions out here at when the larger X value gets, the less comfortable I feel with making predictions. So that's how I wrote this up. Scatter plot 1 goes with, so scatter plot 1 goes with residual plot D. And that is because the original scatter plot gets more varied or more spread out. It fans out as X increases. Okay, so now let's have somebody else tell the other person. Let's see. The evens are going to tell the odds. Which residual plot do you think goes with this scatter plot 2? And why? So make that decision and decide. Go. All right, so let's go ahead and decide what's going on there. Okay, so I don't necessarily get to ask you, but you know what? One thing's interesting. I see in scatterplot 4 and 2, we've got that data like that. I see that in scatterplot 4, the data is more closely, tightly clustered around the line, and in data and 2, it's farther apart. Now, one thing I noticed this year, and last year was the first time I did this lesson, but I think I'm not really addressing. I think, it could be arguable that you have some kind of something like this going on, but honestly, that in this class, we really do not address the trigonometric functions. So I don't feel as though the intent for data 2 or 4 was having this wavy pattern. I think that is nice, even scatter on either side of the line the entire way of the graph. All right. So I'm going to say 2 looks like the more spread out of the ones that have even scatter of them. And so therefore, I think that goes with residual plot A, because that is the one that is more spread out of the 2 that has even scatter. So it does seem to be random scatter, but it is more spread out than scatter plot 4. All right. So now, let's see, that was the evens. So let's have the odds telling the evens which residual plot you think goes with scatter plot 3. Go. And why, of course, and why. Go. All right, so hopefully you caught that you see this curved pattern happening in the original graph, and that then is accentuated and translate to something looking like this in that plot B. So that would be your answer there. Scatter plot 3 goes with residual plot B because the original scatter plot has a curved pattern. It goes up and then back down. So that leaves us with scatter plot 4 going with residual plot C. It is random scatter, and that's nice. Random scatter is a good thing in a residual plot, and it's less varied than scatter plot 2. So honestly, when we talk about the appropriateness, and so I'm kind of jumping ahead to something I'm going to discuss on the next day. When we talk about appropriateness, is a linear model appropriate? Then this situation here, where you have a curved pattern, that's bad, because probably something more quadratic is better, or some other type of function. This is also bad. I do not know really what would go with this. I just know that as you get farther out in the X direction, this is a bad place to be making predictions. So a good indicator of making predictions is where this residual plot has random scatter with no pattern in it. Then what that tells me is that along the whole entire line, the data is nicely scattered on either side of the line the entire way. So if we have random scatter with no pattern, then what I would conclude, random scatter with no pattern, then I would conclude in the original, a linear model is appropriate. A linear model is then appropriate. All right, so we'll talk about that more in a second. So here we've got some other examples. So, a problem occurs in predicting if the linear model is not appropriate, because you can't then just plug your X value into the equation of the line and make a prediction. And here's the thing that I struggled with even when I first started teaching this class. You cannot simply rely on the correlation coefficient value. You cannot make decisions based on the fact that you have a strong correlation. And that is because, as evidenced below, here is something that, we would call this a strong correlation. And look what scatter plot that goes with. It goes with one where I do not feel comfortable making predictions out here in the far x's. So a linear model is not appropriate even though we have a strong correlation coefficient, because as x increases, the y values become more varied. As x is increasing, these y values become more varied, and you have a pattern in the residual plot. So a pattern in the residual plot is bad. That indicates that you should not use a linear model, a line, to predict. Okay, let's look at example 2. So this is one where I have a strong, also very strong correlation. And this is one where I had the random scatter on either side of the line. And so I'm feeling as though no matter what the X value is, I'm going to be able to consistently give an adequate prediction of the Y value. So see, look, regardless of the location of the graph, the data points are evenly spread around the least squares regression line. So I would feel comfortable making predictions using a linear model for this. So a linear model is appropriate. Next, here's this last one. And look there, again, just looking at an R value of 0.94, strong correlation. And you know, that's happening because this data is really nice. I mean, it's tight around this line here. But when you look at the residual plot and it accentuates those residuals, it really makes it apparent that you've got a pattern in that residual plot, so linear is not appropriate. So in this case, we're saying, is a linear model appropriate? No, because a curved pattern appears to be a better fit. If there's a pattern in the residual plot, then a linear model is not appropriate. And I say, and I've said this for a while, I need to make a little tune on that phrase. If there's a pattern in the residual plot, a linear model is not appropriate, because a typical thing that we say is, let me find it and let you write it down somewhere. Down here at the bottom, look. We'll say, yikes, there's a pattern. So if you go to the bottom of page 27, there's actually a song for this. So, yikes, there is a pattern in the residual plot. Therefore, a linear model is not appropriate. A line is not the best fit. And so I'm going to kind of wrap this song, and maybe we'll play I'll put the video of the song also in the links for the substitute to play. I'll put the 2 links to the songs so we can play those after I get done recording these notes. So this one we say, look at our lyrics. Yikes, is it linear? Listen, have you got a correlation coefficient? So this is nice. You know, we say, hey, do you have a correlation coefficient? You know, how strong is it? R is the strength of linearity. We know that. And R squared, we learned last week, R squared is the percent of variability, you know, the percent of variation that is found in the Y. So yikes, is it linear? Listen, have you got a correlation coefficient? R is the strength of linearity. R squared is percent of variability. But here's the key. Here's what happens today. Look at this right here. Can we tell from R? Is the correlation coefficient the singular indicator as to whether or not a linear model is appropriate? And that, as you can tell on the previous page, is no. Can we tell from R? No. You don't know. Residual plot. You must check. Look at the residuals and see if there's a pattern. And this right here, this comes in like chapter 27. So we'll hold off on that, but it comes in the song. But we'll talk about this statistical evidence only with a p-value, linear model. Dun, 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 dun. Linear model. Yikes, is it linear? Listen, have you got a correlation coefficient? R is the strength of linearity. R squared is percent of variability. Can we tell from R? No, you don't know. Residual plot. You must check. Look at the residuals and see if there's a pattern. Statistical evidence only with a p-value. Linear model. Okay, so we'll play the real video or the real music video to you for you after the notes. Let's talk about a last concept. So here, FYI, at the top of this page, this one was one again with a strong correlation. We had nice scatter. It's nice tight scatter, no pattern in the residual plot, so we like that. Now, of course, why is it so important that we identify the model that correctly fits the data? Why do I have to know if linear is appropriate? Because I need to know if using that function, using that LSRL to plug in the X to get the predicted Y, is going to be meaningful to me. That's the thing. Is using a linear function going to be important and meaningful and useful and a good predictor of what's to come? All right, now next thing, last concept of the day, this thing called extrapolation. This is, I'll just kind of give you a heads up, also why sometimes the y-intercept doesn't make sense. So I'll get to that in a little bit, but look here. Extrapolation is good in science, but bad in statistics. In your science classes, you do a lot of trying to make connections based on a little bit of data, and then extrapolating your results, coming to these vast conclusions based on that little bit of data that you have, and so on and so forth. But it is very bad in statistics. So extrapolation is bad. Extrapolation is when you are trying to make a prediction far outside the domain of the data. So far outside the actual X values in the data. And here is a picture to demonstrate that. Look at this. What if all of our data is in this section right here? Well, when all of our data is in that section right there, we go and we fit a linear model to it. And then we zoom in, we do our little residual plot, and we're looking at this thing with our residual plot, and we are pleased as punch that looks like a random scatter in the residual plot, and nice, it looks like a linear model is appropriate. But what happens out here is the function could change. We truly only have information telling me that the linear model is appropriate in this domain of data, these X values from here to here. Making a prediction way out here could get you very far off from actual events, because this function then changes and takes a curve. So it does not continue in a straight line. Look at how far off your prediction could be because of extrapolation. And so, that's why sometimes the y-intercept doesn't make sense. Because let's say you're doing something with the diameter of a tree and its volume. Okay, well, you went out into the forest and you measured all of these trees, and here's the data you got. Okay, well, you know what? That's beautiful. And you get this nice, gorgeous linear model. Oh, poo. That didn't turn out exactly as I wanted it to. I wanted it to be such that it comes out to a lower, let's go here and here. There we go. Let's do that. Okay, so what happens is here's our axis. We've got going from here to here. There we go. Now we're talking. This is our equation of the line, and let's see what happens with this y-intercept. This y-intercept says when the diameter is 0, what's happening to the volume? You have a negative volume. And that's because all your data was in this domain here. So the y-intercept is just kind of a placekeeper, but it's happening way down here. You're actually, its a piece of, its location is actually an extrapolation because it's an x value of 0 is far outside the domain of the data. So that's why sometimes the y-intercept isn't really plausible in the context of the problem. So here is our summary that we want to discuss. First, we look at the data we get, put in the best function that we think will fit. Then we try to use the function to predict, but the future data pattern may change quite a bit now. Don't you extrapolate. Don't you extrapolate now. Future of the data is a debate, so don't you extrapolate now. All right, now, one final thing, which I don't think I've really used this vocabulary much in my lessons, but I noticed, FYI, this is called interpolation, which I think makes sense. This is making a prediction within the domain of the data, and that's beautiful. No problems there. Making a prediction inside the domain of the data. All right. So then, honestly, I can't remember what your assignment is after doing this. So, oh yeah, your warm-up on whatever pages these are, 28 and 29, because doing a quiz is coming up pretty soon. So you're doing 28 and 29. And I'll look on the assignment and decide whether or not you're also doing some of these free responses. And it will tell you on the assignment lesson plans if you're also going. But I know for a fact you're doing this Chapter 7 and 8 Basics quiz warm-up.